PhD student while I was a senior PhD student when I started my PhD at ISI. And I always have looked up to him. When I started my PhD, it was good to know that there was a light at the end of the tunnel, and he was right at the light. And so he was very aspiring, and I used to be inspired that he was at the end. But Lars has continued to inspire me. If you actually look at his contributions to the community, over the last 2 decades, he has been very actively involved in the IETF and the IRTF, which is the research arm of their organization. And he now is leading the QUIC working group. And so when I saw that he's leading the QUIC working group, I reached out to him, and he very graciously and very quickly agreed to do this talk. And so I'm very grateful that Lars is here, sharing, with us what QUIC is and whether it will replace TCP or what impact it will have as the internet protocols evolve over the next decade or so. Lars is also very actively involved in the leading conferences from SIGCOMM and SDI, and is on those committees. So thank you, Lars. Thank you for making time for us, and to you.
Thank you. I'm very embarrassed now. I didn't know I was the light at the end of the tunnel. That is inspiring and also a little bit scary. So yeah, I'm very, very happy for the invitation. Thanks for reaching out. And it was easy to do this talk because you might imagine I've given it a bunch of places. So the slide deck was basically ready. The title actually came from some conference that thought my original, more researchy title was too boring. And so they gave me this, and then I just stuck with it. So the answer is probably not quite yet, if you sort of can't wait for that. So as I said, I'm very happy to be interrupted to do Q&A. I have some natural breaks that I'm going to use to do Q&A in the middle. I'm going to talk a little bit about what is it, what is an internet transport. This is sort of a general audience, networking audience talk. So a bunch of you will probably be very familiar with this already. I'm going to talk a little about the current challenges that internet transports are facing, a little bit about QUIC, some of the design highlights. It's a very complicated fuzzball of stuff, so I'm not going to go into all of it, and then sort of a little bit about what's the current status and what are we currently discussing. And I'm probably going to take sort of Q&A after all of these while we're going. And I think I have an hour, so I hope I don't need that, but let's see. Right, so in a nutshell, QUIC is a fast, secure, evolvable transfer protocol for the internet. And what does that mean? Right, so fast, the goal is to deliver better user experience than TCP and TLS do for HTTP and also for other content. While QUIC originally was designed to carry HTTP, and HTTP over QUIC is called HTTP 3. Microsoft has already a prototype of running at the SMB file system on top of QUIC. DNS is being discussed as an application protocol on top of QUIC. I think somebody's running SSH on top of QUIC already. So there's a whole bunch of other applications that are trying to use QUIC as a transport protocol. Secure, it's supposed to be more secure than TCP and TLS for that content. It's always encrypted. So unlike with HTTP 1.1 and H2, there's no way to turn off TLS. If you're using QUIC, you always have TLS encryption. And the goal is to resist pervasive monitoring more strongly than you can do with TCP and TLS. And QUIC can do this because it authenticates the entire packet, including the header, and it encrypts and or obfuscates most of the metadata that would be in the clear with TCP and also TLS. We want it to be evolvable. As many of you probably know, TCP has become increasingly hard to change. There's some very hard limits in terms of header space and assumption that the network is making about what a valid TCP flow looks like, that is really preventing us from evolving it in a way we would want to. And QUIC is supposed to be a transfer protocol, right? So it's supposed to support all of TCP content and more. We're looking at real-time media because QUIC can more easily support partially reliable traffic. Ideally, it might provide some better abstractions down the line, and it avoids some known TCP issues along the way. And there's a little formula on the bottom. So QUIC is like, it runs on top of UDP. It has congestion control, which it steals from TCP, which is the CC part. we borrow TLS for security, and originally the goal was to carry HTTP, but now we're carrying other stuff as well, and that is QUIC in a nutshell. The summary is that, so my prediction is that the web will move to QUIC first, not surprisingly, that's the big driver for it, and then everything else will. I think this will happen this year for the web at least. We've already seen some very large content providers move to QUIC. Facebook, for example, is running IETF QUIC in production already. So is Google now. Google QUIC has been turned off and IETF QUIC is now run for Google. And we're going to see the CDNs and other browsers deploy it within regular customer builds very soon. And so if you're doing anything with HTTP or TCP or just networks, QUIC should really be on your radar. And I guess it is for most of you, but not for everybody who I give this talk to, which is where that bullet comes from. So what does it mean to be in internet transport? I'm probably going to go a little bit quick here, but you guys know all of this. We can get back to it if there's questions. So the classic version is the internet hourglass. Many of you have seen this, right? Windsurf, I think, coined the term IP over everything. There's a rare picture of Wind without a three-piece suit on from 1994. I think this is the last time he was out of a suit. And this is sort of the classical view, right? You have different physical media on the bottom of that hourglass. Then you have some link layer protocols, and there were many of them at the time. Then you have IP at layer 3, which is this narrow waist. And on top of IP, there's again more flexibility for different things, such as TCP and UDP at layer 4, the transport layer, and then different application protocols and applications on top of that. This is sort of inspired by the OSI model minus some of the session and presentation layers. And this transport layer on top of IP, this is really the thing that provides sort of useful basic abstractions to applications, right? It provides unicast and multicast services, multiplexing of different network flows between the same machines. It provides streams and or messages. It provides reliability, either fully or partially. And there's some flow and congestion control built in to make it work over the internet and establish some fairness. And there's a bunch of other things. So most applications found it hard to implement this from scratch. And so having known good mechanisms at the transport layer that everybody could just use really enabled this plethora of applications that have happened at the time. So this is the modern version of the hourglass. This is not so modern anymore. Now it's from 2015. This is called the Twisted Martini Glass version, which Brian Trammell and Joe Hildebrand, I think, designed. And it's interesting, the link layer is still there, and it's still there's still diversity, although it's mostly Ethernet in some shape or form. But then you have like these two things called IP, IPv4 and IPv6, and they both exist at the same time, and they will likely exist for a long time. On top of that, you have much less like diversity as in the past. Basically, everything runs on top of TCP, and most things then run on top of TLS and HTTP. And applications, 2015 and today, increasingly this is what they're running. The application stack is HTTPS on top of either IPv4 or IPv6 over whatever link layer you happen to have. So the ways is split. There's v4 and v6. TCP is completely drowned out UDP. UDP is mostly used for DNS, right? And even that is not that common anymore. And HTTP and TLS are de facto no part of the transport. And you got web applications that basically run v4 or v6. This is sort of where we were 2015, and this is still where we are today, before QUIC. So what happened, right? Why did we change from the original Windsurf classic hourglass to this Twisted Martini thing? One reason is that transports were really slow to evolve, especially TCP. It's a fundamentally difficult problem to tweak TCP to perform much better. I'm going to talk about this a little bit more in the next slides. What also happened is the network started to make assumptions about what TCP and other traffic looked like and how it behaved, right? This is your middle boxes, your NATs, your firewalls, your intrusion detection systems, your policy enforcers, your traffic shapers, your legal intercept boxes. All of those sort of assumed that a TCP connection looked a certain way, and if you subtly wanted to change that, you found that a bunch of connections didn't work over a bunch of network paths anymore, where a middle box had made an assumption that, for example, you could only ever use the TCP options that were in play when it got deployed. And there's valid reasons for having these middle boxes, right? They try to help and manage stuff. There's sort of friendly ones like TCP accelerators and so on, but they're actually curtailing the evolution that we can do with TCP. And then the web happened, right? So almost all content moved to HTTPS. It's easier and cheaper to develop for and deploy on. It's readily understood. It's amplified by the push to mobile and then to cloud, and it really sort of baked in this client-server assumption deep into the network, right? Which the original internet didn't have it, but with the web, right? There's a client and there's a server, and the client needs to talk first, period, for the most part. So those three sort of trends, I think, sort of led to this internet ossification term that at least in the IETF has sort of become popular. So meaning that sort of the internet has sort of ossified around the protocols, and it's really hard to change them because there's so much baked in assumptions about how widely deployed protocols look like that they become basically unchangeable. Some examples of this stuff, right? So originally with IP, there was this assumption that if you know the IP address of your peer, you can send to that from anywhere at any time, right? As long as you know the IP address, you're good to go. In reality, now we have enforced directionality because of NATs and firewalls, like the client side, whoever that is needs to speak first. And there's a certain timeliness also associated because, you know, when the client speaks to the server then needs to respond to the client pretty soon afterwards, because otherwise, you know, the packet from the server to the client is going to get dropped because something in the middle decided server took too long to respond, you know, invalid flow. Originally, the vision was we would have many protocols on top of IP, right? There's a protocol field or a next header field in the IP header. In reality, if you're not TCP or UDP, you get dropped at pretty much the first middle box that you hit. This was, you know, for example, what killed SETP, which was another protocol that the IETF tried to standardize that kind of sort of looked similar to what QUIC provided in terms of the services to the applications. End-to-end addressing, right? Addresses were supposed to like have end-to-end meaning, and today they're being rewritten all over the place, including port numbers. IP options and TCP options were the evolvability mechanism that we had built into those protocols, right? If you wanted to do something new with IP or TCP, you define a new option in the IETF and you add that to the packet, and the people that understood it could do something. In reality, any option that isn't widely deployed is going to just get killed. And so when we did Multipath TCP, the biggest problem was to figure out how we could make it look like TCP enough so that it would pass through most of the middle boxes. And in general, right, this original architectural vision was that the bits have meaning only inside the layer of the header that they're in. When in reality, the middle boxes just think, you know, they can touch bits across the packet and rewrite them, and it's basically a free-for-all. So really everything that's in the clear in the network will be observed and will likely get modified. Because the network is no longer stateless, right? The network assumes it can track an entire connection from beginning to end, and it can make assumptions about what that connection is carrying, or even, you know, parse the content directly. And so this notion that the data has meaning to the application only is long gone, because the network assumes it can do stuff with the data too. And one the latest sort of or one of the latest trends here is this in-network computing, right? Which has great potential because, you know, you can basically compute stuff for free in the network. But it's really hard to secure this because, you know, there's no end-to-end guarantees anymore. And so there's this tussle here. And with QUIC sort of tries to roll back the control that is trying to remove the network from the equation here as much as possible due to its design. Right. Let me stop here for a second and see if there's any questions about the stuff I talked about so far, and I can take a drink. Right, going once, going twice, let's keep going. I mentioned before that TCP is getting hard to change, and I'm going to talk a little bit about why that is, which should not be surprising to many of you. But so TCP is not aging well. We're hitting hard limits. There's this space for options in the TCP header, and you can have like 40 of them. And a lot of them are already used, right? So if you're a modern TCP stack, you want to use SAC, you probably want to use timestamps and window scale and maximum segment size. And then you already have like, you know, use 30% roughly. If you want to use Multipath TCP, you're going to need to burn 12 bytes. If you want to use TCP fast open, it's 6 to 18, depending on what you use to secure that. So you can see that, you know, a modern TCP stack, the option space, especially during the handshake, is really sort of limited. And very clever people have for a long time tried to figure out how to increase that option space. Haven't seen anything that actually works always. There was a proposal just this week, I think, another one on the TCP-M list in the IETF. Maybe that one is the winner, but kind of doubt it. It's really difficult to evolve TCP. When we did multipath TCP, the multipath part wasn't the hardest. The hardest part was to engineer the stuff so it gets through the network. Because the new TCP must look like the old TCP, otherwise it doesn't make it through the network. And TCP is already very complicated. And if you need to add complexity just so you make it look like old TCP, it's not a good way to do engineering, right? And it's not going to make it makes it simpler. And then there's slow upgrade cycles for TCP stacks. You basically need to update the kernel still. It's gotten better because at least consumer operating systems, that's become painless, but it's still not, you know, zero cost. And for servers, it's still high risk and invasive because you need a reboot or at least sort of, you know, do a pretty invasive maintenance operation. So it's not as easy as, you know, installing a new app. And TCP headers are not encrypted or even authenticated. The middle boxes can still do what they want. There's some options that we defined, TCP MD5, and then the more recent TCP authentication option. In practice, they're really only used for some BGP sessions and not end-to-end for anything else, because key management is hard. So that's, you know, why TCP is not aging well. Middle boxes do stuff, right? This is sort of some canonical examples of a benign TCP accelerator. You know, you split the connection in the middle, and by having 3 different control loops instead of one that has a long RTT.
So the data are correlated, but they're correlated on a workflow level for the TCP.
Right. Sorry, I thought it was a question, but I guess not. So if you do this, you can sort of gain some latency, which is great. But now you have state in the network, and you have problems because if you want to run something new end to end, then there's this transparent proxy there. That's not going to work. But still, this is sort of a benign middle box that actually wants to help you. There's also these things that we know thanks to Snowden, right? There's quantum insert, where the NSA is racing the client to the server, and if they win, you're talking to them and not to the server you want to talk to. And then there's a great paper that is called the Great Canon, that basically shows how the Chinese used a great firewall to do a JavaScript insert that use your browser to attack various other people in the network. And those things are possible because TCP is basically not secure. And the IETF has decided that pervasive monitoring, especially, you know, stuff like the Great Canon, is an attack on the network and the users. And there's consensus that we want to mitigate this. And to many, mitigate means we're going to encrypt the hell out of everything. And that's controversial in the IETF still, but in the QUIC camp, at least, that is sort of really what drove a lot of the design. Right. Talking about QUIC a little bit, since this is what the talk's supposed to be about. This is slides that I stole from Jana Iyengar. They are from the QUIC BOF in the IETF, where we decided to charter this work. And this is when Jana was still at Google, right? And they're from Google's perspective. So if you're Google, how do you make the web faster so you can make more money, right? And this was the stack originally. You had your browser on top, you had HTTP 1.1 and TLS and TCP IP, you had a physical network, and then you had your Google.com servers. And there's a certain latency budget associated with going end-to-end across that stack. So the first thing you do, you build a carrier-grade network. That's what Google did, right? So they had Google.com, they had a Google CDN, and they peered deeply. And so they got really close to the end users in terms of speed of light by removing a lot of the lower layer network overheads. So that helped. Next thing they did, right? You launch your own browser. They did Chrome, then they did Speedy to modernize HTTP that turned into HTTP2, and they did a bunch of stuff to TLS. So that sort of attacked the latency from the top. So again, pretty significant gains. better services for the users and more money for Google. But what's left, right? It's the stuff in the middle, which is TCP and IP. IP can't really change so much anymore. So it's really TCP, the transport, where that is now sort of the low-hanging fruit for gaining more latency. The rest is already squeezed pretty tightly. And this is exactly what motivated QUIC for them. Showed you the slide already. So QUIC is basically this transfer protocol that we built in the IETF now. It's not that new. I mentioned it originated with Google. It's been deployed between the Google services and Chrome since 2014. The SICOM paper that I had in 2017 had a rare graph from Google that actually had numbers on the y-axis. And they said that it made up 35% of the entire Google egress in terms of bytes. And by some estimates, that's sort of 7% of total internet traffic. So that's already pretty significant given that it was only Google and only Chrome at the time. I got numbers earlier this year from the Internet Exchange Point in Frankfurt, and there was lots of hand waving, but I think that the quote would be that on some links, they see 20% of IETF QUIC at the moment, which is nice. On others, they don't, so it's not clear what the average here would be, but at least sort of it's a thing that they see frequently. And if you go to the Cloudflare radar, they show that around 6% of the connections to Cloudflare at the moment use QUIC, which is sort of consistent with the 7% total internet traffic, maybe. So it's a thing already. And I mentioned that this is only some pre-production stuff. So even though Facebook, for example, has deployed it, they still do A/B testing. So while all the apps have QUIC enabled, it's not clear at any given time how much QUIC is actually generated by Facebook. Everybody still wants to sort of debug their stacks, and we're going to see a large increase, I think, towards the end of the year. In the stack, right, this is a similar picture like I've shown before. The old stack had HTTP2, TLS, TCP. The new stack, compared to Google QUIC, replaces the QUIC crypto that Google had built and replaces it with TLS 1.3 that had some features that were inspired by this proprietary stuff that Google did. We're stealing congestion control from TCP. So we are basically specifying a new Reno-style congestion controller in the IETF. Most deployments actually use Cubic or BBR. And the hope is that in the future, there will be new congestion controllers that will be enabled by QUIC because you can freely redefine what feedback you're sending from the receiver to the sender. And it runs on top of UDP and not TCP. Why are we using UDP? It's very simple, right? TCP is hard to evolve. I mentioned that. Everything else is blocked by middle boxes. So UDP is really all we have left. If you want to go through the internet, it's TCP or UDP and nothing else. And so we wouldn't need to use UDP at all. We're not using any of the features it provides. Well, it doesn't really have many features. But we're only using it because we need it to get through the network. Otherwise, we could save the overhead of the header. It's not completely without problems. There's a bunch of middle boxes there that seem to think that UDP is only for DNS. And that means that they sort of enforce short binding timeouts that are much shorter than for TCP. There's some other weird boxes that really only allow UDP on port 53. Those get slowly phased out. There's some short-term issues that we're seeing because TCP performance has been increased a lot by having NIC offloading of various features that are costly to do on the CPU. And the NICs can't do this for QUIC yet, but they're quickly gaining that support. But there's also a lot of benefits. So because we run on top of UDP, we can actually deploy a new QUIC stack in user space. So you don't need to upgrade your kernel or reboot your machine to run a new QUIC stack. You basically link a new library or install a new application that comes with a new library, and you run a QUIC stack. You can also run multiple QUIC stacks in parallel. Different applications can use different QUIC stacks, no problem. And because of that, you can offer alternative transport types much more easily than a kernel-based protocol can do. Why do we need congestion control? It's an absolute requirement if you want to run over the internet. I don't really think I have to go over this. The photo is not a parking lot. It's actually some highway in China during rush hour. And what we're doing for QUIC, I mentioned before, we basically take what works for TCP. We're not doing anything new here. As a consequence, QUIC has segment or packet numbers. We have acknowledgements. We estimate the round trip time. We're doing this pretty much exactly like TCP does. It's a little bit simpler because we don't have like retransmission ambiguity in QUIC, for example. So there's some stuff is easier in QUIC, but basically, if you know TCP congestion control, you kind of know what QUIC does. Why do we need TLS? We need security to run over the internet. We want to protect the users, and we also want to prevent the network from ossifying on the first version of QUIC. We want to be able to evolve QUIC forward. So we don't want to expose anything in clear text to the network if we can avoid it. The consequence is this QUIC has a very, very minimal network visible header, and everything else is encrypted and not visible to the application. We're using TLS because it's very widely used. We can leverage all the R&D that's gone into it. We can also leverage the PKI, so we don't have to do that. We don't want any custom security. There's just too much to get wrong. Even TLS keeps having issues, although TLS 1.3 looks a lot better. It's a lot simpler because it removes a lot of the old optional features. And we want to benefit from the new TLS features that arrived in 1.3, many of which were inspired by Google QUIC. Why are we focused on HTTP? Because that's where initially the impact is. I mentioned before, basically applications are web applications these days. And so everything else is really niche, right? And the web industry is incredibly interested in improved user experience and security for money reasons, right? Plus, there's rapid update cycles for browsers and servers and CDNs. There's also really good A/B testing that they're doing already for various things. So this is sort of an industry that is really modern in its ability to take in new developments and test them out across its user base and server base. So this is really makes it very easy to design a protocol and try it out and roll back if it doesn't work and try something else. And I predict that many other application protocols will follow once HTTP has gone to QUIC. Some details on QUIC, or maybe I'll take another break here and see if somebody wants to ask a question now.
So I had a couple of questions. So it seems right now the route QUIC is going, it's almost sort of an enhancement to the HTTP protocol. The focus is really to optimize HTTP performance on the network. And I was wondering whether when it initially started, there was, you showed the slide where Google was trying to optimize the stack. Did they ever think about putting all these features that they were thinking of within HTTP itself?
I don't know. I mean, they tried to do speedy, right? And they did HTTP 2, and I think they realized that TCP was the limiting factor, right? Because it would still need to run over a single byte stream, and you don't want to use too many parallel connections because then you are fighting congestion controllers, and that actually that motivated it too, because HTTP, which did modernize the HTTP semantics, but still ran over TLS and TCP, had limitations such as head of line blocking, which QUIC doesn't have, and so they couldn't do it at the HTTP layer.
Right. Yeah. No HTTP on UDP kind of notion.
That actually did exist at some point in the 90s. I think I had a Mozilla browser that did that for a while.
Right, because that's what we are doing now. We are doing HTTP on UDP with QUIC. Right.
But back then it was really actually on UDP, but yes. Yeah. I mean, and we really only use UDP because we have to, right? As I mentioned, if we could get through the network without it, we wouldn't. But anything that isn't TCP or UDP has no chance.
I think there's another question.
So Lars, thank you for the introduction and the problem statement. I think when you throw your stones at TCP, one could say that those concerns are all because of its success, and because TCP was what people were using. There was a huge amount of investment in trying to exploit every loophole to make TCP better so I could sell my product. So I think the real question for me, a real question about QUIC is, why will QUIC not be equally ossified 10 years from now? And you've sort of hinted at that, but I wonder if you could comment on what is fundamentally different here than with TCP 20 years ago.
Yeah, I think I have some slides coming up. So the main difference is that all the metadata that TCP carries in the header, like packet numbers and ACK numbers and options, are encrypted with QUIC. So the network in QUIC, the network with QUIC has very limited visibility into what the flow is doing, and so has basically very little ability to, so either they can drop all QUIC or all UDP, right? Or if they are really fancy and keep updating the box, the middle box frequently, they might be able to detect what version we're negotiating and try to allow only certain QUIC versions through. But otherwise, it's an arms race, right? And the hope is that most middle box vendors won't bother.
Okay, so that's a pretty good technical answer, that because it's encrypted, they can't do anything. I thought that was a win too, until Kazakhstan and a number of employers forced people to deploy certificates so that they could decrypt TLS and save their users from their mistaken ways. Why won't that happen with QUIC? And once that happens, are we stuck?
That's a possibility. So for the web, right, browser certificate pinning helps. So the browsers will basically, for big websites, only accept the certificates that are authenticated by DNSSEC. And so even if you install a wildcard certificate and man in the middle TLS, because the server, the middle box, can't present the pinned certificate for the website, the browser won't accept it. But it really depends on this sort of web PKI feature, and it's tied to the web. It's possible for QUIC. So I'm going to get to this a little bit later. So if you control one of the endpoints, which these deployments force onto people, right? Many QUIC stacks allow you to export the keys similar to TLS with this SSL keylog file format that I think originally came from Mozilla, but is now widely supported. So if you set an environment variable and you run your browser, it'll write the keys into a file, and then you can import that file into Wireshark, and it'll decrypt stuff for you. And you could sort of, ship that key into the network and then have a network box do the same. But you need to basically, you can't do it transparently. You need to, the user is aware that this is happening, unless you're sort of Trojaning their machine without telling them.
Well, or some of us run IT provided machines that have all been Trojaned.
Yes.
Okay, but thank you.
Those are non-trustworthy computing devices.
So we have another question from Wes.
Hey, Lars, I'm glad you're here today. It's funny, 20 plus years ago in the IETF actually presented a analysis that I did when the network management group was trying to switch protocols and stuff like that. And I was showing how UDP actually succeeded with retries much more frequently in high loss networks than TCP, which just sort of eventually fell over. But I guess my question is, if it seems like the whole world is, if we move most protocols to QUIC, right? If we end up, everything's now going to go over QUIC, what sort of helpful TCP options are we giving up when restarting with a new transport? It seems like we're headed for a one-size-fits-all type of approach. And, if we're optimizing for HTTP, are we sacrificing things for other protocols where they may actually, benefit from other stuff we're leaving behind?
That's a good question. So it's actually, I would actually argue it's the opposite, because so QUIC, there's a document called the QUIC invariance, which is basically the thing that cannot change as we evolve QUIC forward and define new versions of QUIC. And there's very, very few of those. It's basically, how do you negotiate versions, which versions you're speaking, and there's a few things in the network visible part of the QUIC header that need to sort of stay where they are, But otherwise, after version negotiation, because it's all encrypted, you don't actually have to speak IETF QUIC at all anymore. because the network just sees random bytes with a very small header in front. So it actually allows much more diversity in terms of tailoring your protocol to the application. Some of this might happen with QUIC. So one of the things that's different, and I don't think I have a slide on it, is that there's no defined API for QUIC, right? So there's no socket API equivalent that an application codes against. If you're building an application on top of QUIC, you are picking a QUIC stack and you're using the API that QUIC stack provides. And if you want to switch QUIC stacks, you're in for a lot of pain because the APIs look very different.
Some might argue that's a bad thing, but
it's a bad thing, but it's
a trade-off.
The world we are in, because that's how you gain the performance. The abstraction, the socket API abstraction, right, is great, but it's also simplistic. And if you are worried about maximizing performance, you want to have your fingers, as an application, you want to have your fingers deeper into the scheduling of transmissions and the reception of packets than the socket API allows you to do. And so we're giving something up here. But let me maybe run through the next section, because it has a bunch of slides related to what we talked about, and we can come back to that afterwards.
Yeah, we have 2 questions in chat, and I see there's another, John's raised his hand again, but so that we don't run out of time, we will keep more for discussion later, but we'll let Lars continue.
And we have about 20 minutes, right?
Yes.
Okay, got it. So this will hopefully be quick. So I mentioned this minimal network visible header. So QUIC has 2 packet types. There's the long header packet type and the short header packet type. The long header is basically only used during the handshake. After use, you use the short header. And with QUIC, the network really sees the type of packet. Is it a long header or a short header packet? In the long header, there's the QUIC version that is visible. And there's this thing called the destination connection ID. So QUIC connections are not identified by IP address and port number or 5 tuples. There's a 0 to 160-bit connection ID in the packet, and you're using that to associate packets with connections. That lets you to, for example, survive net rebinding events and so on, because the connection ID don't change. There's a packet number in those packets that is obfuscated from the network in the sense that we are XORing an AES of the last 64 bytes of the packet over the packet number, so that if the network wants to see the packet numbers, it has to undo that operation, and it has to parse the full handshake to get the keys out. So it's not security, but it's a pretty awkward obfuscation for the network to undo for every packet. If you compare that to TCP, you basically see the acknowledgement numbers, you see ECN information, you see timestamps, you see all the options and so on. So metadata is much reduced. And the entire QUIC header is authenticated with AEAD, so it's not modifiable, although it still has some parts that are clear text. Version negotiation, this was originally part of the spec. It got kicked out and is now an extension that everybody sort of will implement because we have to. It's currently under redesign. The graph on the right is from the University of Aachen. They're doing these QUIC measurements, and they've done them for a long time. This sort of shows over time which QUIC versions they've seen in the network traces they looked at, and I basically put it up to see that QUIC versions get deployed and undeployed pretty frequently, and we're gonna probably see continuation of this. So every 3, 4, 6 months, you basically see a new QUIC version ramp up and then ramp down. A lot of that correlates to when the IETF draft versions were released, but you also see there's some Google QUIC still out there and some other private. Move fast on the bottom, that's the Facebook stack. So there's some private versions that are being deployed and undeployed. We have 32-bit version fields, so we can be really aggressive in using new version numbers. IP has 8, TCP has 0 bits for version number, so we don't have to be frugal with those. It enables really vendors to do proprietary versions of QUIC. The hope here is that they will come back to the IETF with the things that work for them, and we can sort of standardize it so others can implement it and benefit from it. But it depends on whether they want to do that. My guess is they would. As I mentioned before, there's very few things that are invariant that can't change from one version of QUIC to the other. So Some of those examples are the location and the length of the version and the connection identifiers in a long header packet can change, because that's how version negotiation is done. And same for the short header packets. And the version negotiation response of a server cannot change. So if you're a client and you want to speak a version to a server that the server doesn't support, it needs to know what to tell you to try something else. And that is not changeable from version to version. Everything else is really version dependent. And QUIC is sort of trying to apply this thing called, in IETF speak, it's grease. So basically, if there's unused code points in a packet header somewhere, you got to randomize them. Traditionally, right, in RFCs, we always said, sender should set to 0, receiver must ignore. What happens with those code points is that nets and middle boxes check if they're 0, and if they're not 0, the packet gets dropped. And that means later on when you want to use them, you can't. This is why we're applying grease, which means anything we're not using, we're still randomizing so that the network doesn't assume this will always be 0. There are two types of handshakes in QUIC. This is a feature of TLS. So for when two peers, server and a client, first handshake, they need to do a little bit longer handshake. During that longer handshake or after that longer handshake, the server can give the client a cookie. And if the client wants to speak to that server again, it can include that cookie and doesn't need to go through the rest of the handshake. That's a huge latency win in many cases. So basically with QUIC ZeroRTT, which is the fast handshake, you need 2 messages and you're good to go. And this sort of fast handshake also helps with NAT rebindings or timeouts where the connection breaks and you need to re-establish a new connection. That's really fast with QUIC. With TCP, you would need to do 7 messages. So it's a much more visible event. There's a little caveat here that the ZeroRTT, because of the security properties it has, you can only use it for idempotent requests. I think everybody's ignoring that, unfortunately. And there's really no way for it. The application needs to sort of know whether a handshake with ZeroRTT or not, and respond accordingly, which is not typically done, unfortunately. I mentioned that the header has very little things in it compared to TCP. QUIC is a frame-based protocol. So everything else is frames. That includes metadata, like acknowledgements, includes data like stream. There's a whole bunch of other frames that are used to negotiate how many parallel streams can you open inside of a QUIC connection. What are your flow control credits for various things? What connection IDs are you making available to the peer for use, and so on. And then there's these path, challenge, and response frames, which are used when you migrate a QUIC connection from one path to another to authenticate that you're talking to the same peer you talked before. But it basically makes it pretty easy to extend QUIC because you just define a new frame type and define what it means. You can negotiate during the either during the version negotiation or during the TLS handshake whether a certain extension frame type is supported. And if both sides agree on that, they can use it. One caveat compared to sort of lots of IETF protocols use TLV, type length value constructs, which means that if you don't understand something, you can skip over it because you have the length. QUIC frames don't have length fields. So an implementation needs to parse all frames. It's not possible to skip over something that you don't support. So you can't really lie about whether you're supporting something because otherwise you can't parse the rest of the packet. But otherwise, it sort of works like TCP, right? Packets have numbers and ACKs carry received packets back to the sender. There's multiple streams in a QUIC connection. This is similar to SCTP, who has the same concept. There's up to 2 to the power of 62 different streams that are possible, so you don't have to be frugal with those either. Congestion control happens at the connection level. Connections are also flow controlled. Streams are also flow controlled. They can be opened by either end. They can be unidirectional or bidirectional. This is sort of mapping some HTTP semantics into QUIC, which I'm a little bit unhappy about, but it is what it is now. And at the moment, streams are always reliably transmitted. I mentioned before that partial reliability is a feature of QUIC. It's going to be soon, but not yet. And you sort of negotiate over time how many streams you're allowing the other side to open. and how you prioritize the streams. I mean, basically, how do you decide what data are you sending at any given time into your different streams is completely up to the application. Let me just run through this little last part really quickly. It's being standardized in the IETF. Many of you participate there. We are, if that means anything to you, past ISG approval. So our specs are with the RFC editor, getting the T's crossed and the I's dotted. I kind of guess they'll probably be out around April, maybe May, who knows. But basically, there's not going to be any large changes to QUIC anymore. We have 20 plus known implementations. Many of them are open source. Everybody who sort of is somebody in the web has an implementation, it seems like. There's two logos missing that you might expect here. One is Amazon and the other one's Netflix. Amazon is looking at QUIC for some things. I think the CDN part, forgot the name, but they have not participated in the interops, and we don't know whether they have their own implementation or if they're using somebody else's. And Netflix has a pretty highly optimized TCP-based engine that they don't really want to get away from. But I think they're looking at QUIC for the application, sort of the Chrome that renders the player, because user experience matters. But the actual content for Netflix, I think for the foreseeable future, is going to keep going over TCP. We sort of have this interrupt status that we're sort of manually filling out. So there's clients are vertical, servers are horizontal, and we have defined test cases. And if something passes, you put the letter into the spreadsheet. Manually, for a long time, there's now also a really cool automated interrupt testing via Docker and NS3 at this URL. So if you have a QUIC implementation, you make a container available that conforms to a bunch of stuff. And you make it part of this, and then we run this with GitHub Actions every 6 hours, every server against every client through all the test cases, and generate this matrix sort of on the fly. And because we're running this in Docker, we can basically plop an emulated NS3 network into the middle, and then create cross traffic and various other impairments in a predictable fashion. And we can sort of create test cases that you know, can challenge an application or a QUIC stack in a reproducible way. So this is pretty exciting, and I think there was a paper at the Epic workshop we had last time at SIGCOMM about this. Next topics. Multipath in QUIC was supposed to be part of QUIC version 1. Most people decided that this connection migration ability that QUIC has is 80% of what they need, and Multipath is complicated, but it's still being discussed. There's a bunch of people that come from the Multipath TCP crowd that really want to do this. It's not quite clear how much energy there is in the working group overall. We're going to see more applications on top of QUIC. I mentioned that before. There's a lot of work on performance, both like NIC performance, getting like to 10 and 100 gigabit speeds. There's also performance questions around like satellite links, especially geostationary, where these TCP performance proxies were really important. And with QUIC, you don't have those. It's not clear what we're going to do here. I mean, I think we're going to see a whole bunch of extensions to QUIC for various, to enable various applications better. One thing I want to mention is this ongoing discussion that we had in the beginning of QUIC and still do, which is encryption versus something else. So I mentioned that QUIC is really aggressively trying to encrypt everything. And network management, there's claims from various operators that they have network management systems that rely on observing TCP header information in real time and to calculate loss in RTT information. Other operators say, they don't have these systems and they don't need that information. But the operators that do claim to have these management systems are worried about this loss of transparency or loss of information. And there's this trouble or there's this concern that encryption will be troublesome for some of these operators. There's this proposal in QUIC called the spin bit, which is it's a method for a QUIC client and a QUIC server that participate in this optional feature to expose the end-to-end latency to the network in a way that doesn't leak other information. and there's proposals to extend this sort of voluntary sharing of information with the network to also include like loss information, but it's not standardized yet. But it's really unclear who needs this, and even if people would need it, most stacks don't want to implement it because they're concerned about the leakage of even this little bit of information. I think lots of the big providers have been burned by networks doing things to their traffic. And there's uncertainties here, right? Because if you have this spin bit, which is not tied to how QUIC works, it's not used by the QUIC state machine at all. It's just information that's stuck on the outside of the crypto envelope, so the network has something to look at. It's not clear why the network would trust this, and what the incentives are for deploying this, and what are the penalties if something doesn't deploy it. The other thing that might be more interesting to some of you guys who are measurement researchers, right? There's this long-standing ability for researchers and others to measure the network and understand what's going on and use that to inform the evolution of the protocols. That is hard with QUIC. Sort of passive measurability somewhere in the network, which was a key factor to this, is basically out the door with QUIC. You need to be in control of one of the endpoints in order to get the keylog files to decrypt the traffic. If you want to do passive measurements, you still need to buy in from one of the endpoints at least. And the question that's been raised by some of the researchers in the IETF is whether we're giving up something fundamental here and we should really sort of pause and think. Other researchers have said, we're past the point where passive measurements are very interesting and it's all active anyway. And if you're an active measurement, if you have an active measurement approach, you control the one endpoint, and so you don't have that problem. But it's going to be a different world where network traces taken by a backbone network all of a sudden aren't all that interesting anymore. If you think back to the 90s or the 2000s, that was like all of IMC, right? Last slide, if you want to participate, we have a working group. This thing, the IETF exists, you all know this, I don't need to talk about it. There's a whole bunch of stuff on GitHub, both the QUIC working group are on GitHub and also many of the implementations are hosted there, so you can just interact with people there. And I didn't put it here, but we have a Slack channel. If you go to quickworkinggroup.org, you can join that. There's actually quite a bunch of researchers on that Slack channel, and I recommend that if you're doing anything with QUIC on the research side, because you can actually talk to the people who run the stacks in production and ask them questions about, hey, I measured facebook.com to do this. Can you tell me why? And they'll be very interested because they're trying to optimize their things. So do that if you're interested in this. Thank you. Questions?
So we have 2 questions in the chat. And I can.
Now I can maybe pull it up because I'm not. Is it from Harun and Ganesh?
That's correct.
Okay. If QUIC usage increased, then do we face any issues for UDP over DNS? No. Maybe Harun wants to say why he's concerned about that. I don't see why that would be a concern. Second part is firewalls pass HTTP. Right. So if the firewall is deployed together with the server, for example, the server side could make the keys available to the firewall in order to allow it to do DPI on the stream. Without that, the firewall can only look at the little information that's exchanged during the handshake. That's not encrypted. There's actually quite a bit of work on this. It's mostly focused on load balancers for the server side. That sort of you could use something similar to that to also deal with firewalls. But I think most deployments actually would put the firewall together with the QUIC server side. Ganesh's questions. How different is content caching with QUIC versus TCP? I mean, content caching is a HTTP level thing, and that is unchanged from the underlying transport. Multi-connection aggregation out of order. That's right. So QUIC with TCP, right? You have head of line blocking, meaning if you are transmitting multiple objects over the same connection, and if there's a loss that affects one object, the TCP stack will not deliver further data to the application, although that data belongs to different objects. QUIC will. That's the benefit of QUIC, right? So the stream that had a loss will need to wait until that loss is recovered from before that particular stream can make progress, but the rest of the connection can make progress already. That's one of the big benefits. And John had his hand up from before.
No, I'm good,
Go
thanks.
ahead.
I got my question before.
All right.
So one question that sort of comes to my mind is, if as we move away from TCP, if and now there is this local decision people will make, application-wise in terms of what congestion control they want to use. Will we have another collapse, the internet collapse as we had earlier?
Yeah, I doubt it, right? One reason why is simply the structure of the internet is such that it's basically only the access network that is the bottleneck, right? And so that means that typically, if there's a collapse, it would sort of it affect one application you're running being unfair to another application that you're running, but it's not necessarily the internet that would suffer. The other reason is that the people who are pushing a lot of bytes on the network are incredibly sensitive to the level of service they're providing. So there's very fine-grained monitoring in order to detect like tail latency changes. And so if a congestion control bug were to escape, it would be found very quickly, and they would basically roll back to an earlier version. We've seen this quite a few times, not because of congestion control, but because of security issues, where Google has basically yanked a Google QUIC version and went back to an earlier version. And I think Cloudflare did the same thing recently with their QUIC stack. So, but I think the reason is that the people who push the bytes these days are very few, and they have highly optimized monitoring systems. We're not in the state where people without that would be in a position to send enough bytes to really matter.
We're exactly at an hour. I thank you again, Lars. Thank you for making time to do this. We deeply appreciate you making time to share and get us really sort of thinking about QUIC systematically, because I think some of us are working on projects that are going to come across QUIC and try to figure out whether we have any insight into what the application is doing if we have only QUIC traffic. So based on your talk, I think we have quite a challenge ahead of us. Thank you again.
It's a new topic area. So there's the paper topic plus QUIC is again publishable. It's a good time to be an academic.
Exactly. It's a luxury. Yes.
All right. Thank you. That was very nice to be invited to talk to you guys.
Thank you.
Thank you very much.
Bye-bye.